Let's talk about work. Work is the transfer of energy. Energy can be transferred into a system or out of a system. Let's take an example. Take a slide, and let's put a person on the slide. What good is a slide without a person? And let's make it a girl. Let's give her a little more hair than that. There we go. And let's say she's 20 kilograms, and she starts at a height of 20 meters off the ground. And we want to know how far she'll slide here before coming to rest. Because, and I should point this out, the slide has no friction, but down here we have friction. And the friction has a coefficient of 0.5. So right here is where the friction starts. So we want to know what this distance is here. And we can use our knowledge of work to get the answer. Work, by definition, is equal to the force vector dotted into the distance vector. If you don't know what a dot product is, don't worry. What this is telling you is very simple. It says work equals the component of force in the direction the object is moving. So it equals this. The x component of the force multiplied by the displacement in the x direction. So, for example, I'm applying a lot of effort to this table, but I am not doing any work because the table didn't move. My force is this way, and I'm trying to move it this way. It's not giving me any work. There's no energy being transferred from me into the desk. However, if I pull at an angle, then this component of force multiplied by the distance that I move the table, that equals the amount of energy that I've transferred in to the desk. So let's go back to our example of the slide. If we want to know how far she slides before coming to a rest, we can use conservation of energy combined with our knowledge of work. And we always start with the initial energy equaling the final energy. Well, what is the initial energy that she starts with? It's all potential energy. Let's assume she starts at rest, like you do on most slides. So she only has potential energy here. And then where does that energy go? Well, it goes into the work done by the friction. So her energy is transferred out of her into heat, sound, and breaking up some molecules here. So let me be clear, the energy of the universe stays the same, it's conserved, but her personal energy is reduced as she scrapes along here. So she starts with mgh of energy, which is 20 kilograms times 10 meters per second squared times 20 meters. And that equals the work done by friction. So that's static friction multiplied by the displacement. And so 20 times 20 is 400 times 10 is 4,000. And it's 4,000 kilograms, meters squared, seconds squared, which is a joule. And then that equals, well, what's the definition for the static force of friction? It's μs times the normal force, and then again times the displacement, which we want to find. Let's go up top here. So now plugging in the numbers on the right side of the equation, we have 0.5 multiplied by the normal force. We got to find our normal force. Well, recall, it's in this position we want to find our normal force. So it's not too difficult. Let's draw the free body diagram. We have the normal force going up, her weight going down, and the force of friction this way. So you can see in the vertical direction, the normal force has to equal her weight. There's only two forces. She's not accelerating up or down. So these two have to balance. Therefore, the normal force is just mg, which is 200 newtons. So I now have 0.5 times 200 newtons times the displacement, and we can solve the problem. 0.5 times 200 is 100. And then if I just divide both sides by 100 newtons, well, 4,000 divided by 100 is 40, and a joule divided by a newton is a meter. These guys cancel, and I have the answer. She'll slide 40 meters before coming to rest in this situation. Means she must have been going too fast, and I'll leave it to the viewer to figure out how fast she was going right here. I'll give you the answer. It's 20 meters per second.